Hello and welcome to the Engineering Dynamics lecture series. This is lecture 1. I will start from chapter 11, Kinematics of the Particles. As you already know, the textbook that we are using in this lecture series, it is Vector Mechanics for Engineers. We are starting from Dynamics section of this book. Before moving forward, the first thing that we need to know, this is just a reminder, is the units. In this course, we will use both SI and US units. So different examples, different units. So as a reminder, you already know that in SI units, the length is meter, in US, this is feet. Time is second for both units. For both systems, force is Newton for SI, and in the US unit, the force is pound. The thing that you need to be careful is the mass. Mass is kilogram in a SI unit. In the in a SI system, in a US system, this is slug. To have some feeling about the value of the slug, that is the simple example is telling that Newton's second law is telling that F is equal ma. When we are talking about the weight, is equal mg. G is the gravity acceleration. So this is telling us that 32.2 pound weight uh, is equal one slug multiply 32.2 gravity acceleration. The unit is feet divided time square. So just keep in your mind the unit of mass in SI unit is slug, because this is the thing that we usually forget about. Okay, moving forward to the kinematics of particles. First, we are introducing you the rectilinear motion of particles, or we usually call it linear motion. The definition is if the particle is moving on a straight line. You can see here in below, I have two examples, A and B. Both particle is moving in a straight line in the x-axis. Definition of position is another important thing that we need to know. The position is distance of particle P from the origin O. So when we are talking about the position, all the time we need to first choose our origin, and also we need to choose our positive direction. What is the straight line and what is the positive direction of that? Then that position P, position of particle, can be positive value or negative value. For example, in case A, particle is located on the right hand side of the origin in the positive direction, so the value of the position value x is a positive. In case B, this is in a negative direction of positive axis, then the p prime is negative value. We can continue with the velocity and acceleration. You know, all these topics you already heard a lot in physics, but this is just a warm up to be sure that we should be all in the same track. Okay, let's say at time equal t, particle is located at that point, at this point here, and the position of that particle is x. Then after delta t time, the particle is moving and now stays here. And it travels delta x. So since we have some movement, we are able to define a velocity. And first we are starting with the definition of average velocity during this delta t time is delta x divided delta t. How much displacement that we have divided by in how fast the particle passed this delta x. That is the definition of velocity. Out of that, we are able to define the instantaneous velocity when delta t is very, very small. We would like to see the instantaneous velocity in a short amount of time. And if we just, and we are able to write it in a differential form as well, v is equal dx over dt time derivative of displacement, and that will be our definition of velocity along the time. Velocity, like position, can have positive or negative direction. If the particle is moving to the positive direction, then the velocity is positive. When it's moving to the negative direction, velocity will be a negative value. Acceleration, assuming that at time equal t, particle has a velocity v. After delta t time, the new velocity is, the velocity difference will be delta v. So again, we are able to find the average acceleration as delta v over delta t. Instantaneous acceleration is delta t over delta t, delta v over delta t. When delta t is very small, again, we are able to write it in a differential form. That will be our acceleration, which is in this form. So there are different ways of presenting acceleration, and it's important to know all of them because it's very, very useful. The first time is just an equation that I already drive it for you. But we already know from the previous slide that v is equal dx over dt. So what we already have is a is dv over dt. If I just replace it with this value, that will be d dt dx over dt. I can rewrite it in this form, d2x over dt2. That is the second derivation of acceleration. So that's why the second type of definition for the acceleration is existing. A is equal first derivative of the velocity or second derivative of displacement. There is a third type that I haven't put it here because I wanted to discuss it in the lecture is this form. Look at this again. A is equal dv over dt. I want to write it in this form, dv over dx, dx over dt. Can we say that these two forms, they are exactly the same? They are the same because this dx, we can cancel, they will cancel out, and the final answer is dv over dt. So whatever we did here is correct. Let's continue. Now I would like to just keep dv over dx, but rewrite dx over dt as velocity. This is a very important way of, type 3 of presenting acceleration is dv over dx multiply velocity. Sometimes in some problems, inputs and outputs, given outputs, given inputs and required outputs, they are only acceleration, velocity, and displacement. And nobody talked about the time. So in this case, I recommend you to use this formula for the acceleration, because in this way, you see in a third type, there is no time. It's all about acceleration, velocity, and displacement. So in those examples, you will see you should use these types of acceleration. Definition of the acceleration. Acceleration can be positive or negative values, but there are four different scenarios. For example, starting with the case A, particle has the velocity v. This is already positive value. After delta t, the velocity increased to v prime, but still in a positive direction. So if I want to find the delta v, we can find it in this way: v prime minus v. We already know that this is a positive value. Delta t is also all the time. In this case, this is a positive value. Delta t is always positive value. So the acceleration is delta v over delta t. This is positive value divided positive value. Result is a positive value. So the acceleration here is the positive value. But let's see case C. Velocity, the initial velocity is v. Then after delta t time, it decreased to v prime, but both they are positive number. Tell me about the sign of delta v. V prime now it's smaller, so v prime minus v will be a negative number. Delta t positive. From here we can say that acceleration is a negative number. So that's why this is existing, and since it's the negative number, we just write it in this way to the left hand side. That will be your task to think about case B and case D, do the same analysis as I did, and find why the acceleration in case B and D is minus, plus, and minus. Okay, few words about the motion of the particles. We said that the motion of the particle is known if we know the position of the particle during the time. For instance, this is the x-axis. If we know that the particle is here at time equal t0, this is a position, so we exactly know the position. It's here at t equal t1, it is here t equal t2, it's here at t equal t3. So in a continuous or infinity number of times, or in a continuous time, if we know the position of the particle, then we can say that this is checked. We know the motion of this particle. Let's move forward for the first example. The position of the particle as a function of time is given. So we can say that we know the motion, because for each time we know the position. So the motion is known. It's asking to determine the time at which the velocity is 0. Displacement, or the position is given, so it's t power 3 minus 6t2, and continue. The first thing that we can do is finding the velocity and acceleration. Velocity is the first derivation of the position. So if we just take a derivative of this equation, time derivative, for example, t power 3 will be 3t2. That is our velocity. And if we continue, take a second derivative, that will be our acceleration. Part A is asking the time that the velocity is 0. So we already know the equation for the velocity. We just simply put it 0. Then we will find two answers for this equation because we have t power 2. One is t equal -1 and the second is t equal 5. One of these answers are wrong, t -1. We don't have the negative time, so the only true answer for the time is 5 seconds. Part B is asking determine the position and distance traveled by the particle at that time. At that time means when t equal 5 seconds. Okay, so it's asking us to find the position. We just simply drag the first equation and simply put t equal 5 seconds. Then we are able to find the position. It's also asking about the distance traveled. The distance traveled means let's find the position, initial position of the particle and see what is the position of that after 5 seconds. And the difference between those, that will be the distance traveled by the particle. So it's the x-axis, the particle is here. That is the origin. So that is my, let's say, x at 0. After 5 seconds, it's here. That value here, that is my delta x, or distance traveled, or displacement. So the initial x0, how to find it? We can just simply use this equation and put t equals 0. And you will see that they will cancel and only this 40 feet will be there. Okay, that will be the answer for the distance traveled. If we use some computer tools like MATLAB to plot these three, displacement, velocity, and acceleration, that will look like this, and we can just double check if everything is fine. For example, we already found that at t equals 5, velocity is 0, and you can see exactly here at t equals 5 seconds, the velocity is 0. And also we know that the velocity is the slope derivative of displacement or slope of the position plot. So you can see at t equals 5 seconds, at this point, it is a horizontal line. Slope is 0. That is telling us that the velocity is 0. The second example is talking about we have a ball. It's about 20 meters above the ground. We would like to throw it upward with the initial velocity of 10 meters per second. We already know that after throwing the ball, the only acceleration applied to the ball will be the gravity acceleration, g, and the value is 9.8. The direction of g is to the ground. So if we assume that this is our y, this is our positive direction. Gravity is a negative direction, so that's why the value is negative 9.8. Okay, let's go back to the example. Part A is asking us to determine the velocity and elevation of y as a function of time. That's perfect. We are starting with our simple equation. Acceleration is dv over dt. Because the acceleration is given acceleration is negative 9.8. What I do in this step is keeping dv in the left hand side and bringing dt to the right hand side. I need to multiply it. That will be negative 9.8 dt. Then I take an integral. What is the border of the integral? For example, for a time, we are starting from time equals 0 to the current time t. We should do the same for velocity because left-hand side is integral over velocity. So we should find the initial velocity and the current velocity v. So again, I'm saying in the time, in practice, this is t0, but we already know that t0 is 0 seconds. So just like we just simply put it t0. So that's why this line is existing. If we complete the integral, the dv will come out of integral as v, and then we can apply this border, and also dt comes out of integral as a t. So, and then applying this border, that will be the next line, that is v minus 10 is equal minus 9, 8t. That will be minus 0 because this time is 0, but we just simply don't write it. Okay, that will be the equation for the velocity. This is the thing that they asked in part A, and also they were asking us to do it for the displacement, for the position. So we know the dy over dt is the velocity. We already know the velocity. So exactly like acceleration, do the integral, apply the border, that will be the elevation or position as a function of time. So we are done with part A. Part B is asking us to find the highest elevation and the ball can reach. So the important thing to know about the elevation is, for example, if we throw the ball up there, it will go up and come down. So that is the direction. When it comes down, is also this way. At some point, it should change the direction of the motion. So we all know that we just have a physical understanding about this problem. At this point, when it wants to change the direction, the velocity will be 0. It will stop for a microsecond and then come back. So this is important thing, and that will be our highest elevation as well. So at the highest elevation, we know that the velocity is 0. We already know the equation of the velocity from right hand side. Let's call it equation star. Based on the equation star, if we put v0, we are able to find the time. If we are taking the equation double star, that is our elevation. Here, whatever time that we found in the last line, we just update it in the elevation equation, and then that will be our maximum elevation. Part C, I'm asking you to think about when the ball hits the ground. What is the specification of the ball when it hits the ground? You already know. Elevation will be 0. Think about how to find part C of this problem. Another example is talking about the bicycle shock absorber. It contains the cylinder and there is a piston in it which is traveling in the oil filled cylinder, of course. So it's telling us that when the front tire goes over the bump, the cylinder will apply, it will is given an initial velocity v0. Okay, that's given. Then piston will start to accelerate, and the acceleration rate is given. A is equal to negative kV. What else is given? And it's telling us at time equals 0, the position of piston is 0. Part A, we plan to determine the velocity as a function of time. Okay, we would like to find the velocity as a function of time. We already know A is equal dv over dt. A is given, dv over dt is there. What I do, I just keep whatever velocity variables in the left-hand side, any time variable in the right-hand side. So that's why I have to bring, I can just keep dv and dt over there and bring v dv here. So that's why that equation will be like this. And the next is taking the integral in both sides. You already know time goes from 0 to t, velocity v0 to the current velocity. If we take this integral, if we solve it, we end up with a logarithmic value. ln v over v0 is negative kt. One step more, we can write this equation in this form. We can say that v over v0 is in exponential form is equal to negative e over negative kt, or we can say that velocity is v0 e minus kt. That is the part A of the question. Part B is asking to determine the velocity. It's perfect. Velocity we still know. It's dx over dt. We already found v in the previous line. Just put it there. Do the integral and then solve the integral. That will be the solution for the displacement. The way that we are solving the integral, we assume that we all passed the math course, so that's why I shouldn't spend so much time on the derivation of these integrals. Okay, for us it's just important to understand the physical meaning of these systems. That is the position as a function of time. Part C is asking to find the velocity in terms of x. Do you remember type 3 of presenting acceleration? I said that we are able to present it in this form. Sorry. dv over dx multiply v. So here it's not talking about the time in part C, so why not to just use this formula? Acceleration is given is equal v dv over dx. Keep, and then these v's, they will cancel out. What remains is dv is equal negative k dx. Take the integral, solve the integral, and then we will find the velocity as a function of displacement. So in this case, you need to go through the third definition of acceleration. So that should be your strategy as well to any example that you see. First, you should know that we have very simple system of equations. We already know only one definition for the velocity and three definitions for the acceleration. These three definitions we should able to solve any problem in the kinematic of particles. So keep in mind, we don't have anything else. Everything is starting from these few equations. But we should able to generate some special cases and use it whenever we need it. One of those special cases is uniform rectilinear motion. What does it mean? That simply says that when the particle is moving with a constant speed, that is telling us that dx over dt is a constant value, or it's v. So we can take the integral of that. Velocity is a constant number, so we just keep it simply out of the integral because it's a constant value. We take the integral, dx will come out of the integral as x, dt will be t. Applying these borders, we end up with this equation. That's important to know when the velocity is constant, when the particle is moving with a constant velocity. This is the formula for the position. X is equal x0 initial position plus vt. From now, whenever we know in the problem when the velocity is constant, simply that is the formula for the position. Also, in some case, when the acceleration is constant. So in this case, dv over dt is constant value. If we take an integral, a will come out as a constant value. If we solve it, we end up with this form for the velocity. So this equation is telling us that the velocity as a function of time is equal to v0 plus at. Okay. Also, we know that v is equal dx over dt. If we just update it, that's telling us that taking us another integral, that will be the equation for the position. We can find it from there. You can think about how we reach out to the second equation from the first equation. And another important equation that we would like to use is this one. Again, you can see here, this is exactly like a third definition of the acceleration. We don't have any time here, so we are able to find the relationship between velocity, acceleration, and displacement without involving time. So keep in mind, you can use all these four equations that I presented. Make sure to drive this equation, second equation by hand, and also think about how they find the third equations. Third equation can be the combination of this first and second equation, and also it can be driven directly from this definition, dv over dx and multiply v. This is the way, this is also another way to end up with this equation. So I strongly recommend you to drive this and see if you are able to find the same values or not. But we will, in our examples, if we have a special cases like constant velocity and constant acceleration, we will use these equations. Also, another special case that we can have several particles. They are moving independently. Let's say we have two balls. One of them we are throwing upward. The another one we throw it downward. So you can see they are two particles. They are moving independently. So we are able to write the equation of motion for each particle independently. But when we want to analyze those, we would like to, for example, what is the position of each particle in respect to the other? Then that will be the definition of the relative position. For example, if the particle A is located at, the position of XA, if the position of particle A is XA, here. When the position of particle B is XB, what is the relative position of particle B with respect to A. I can say that this is the way how I can write it. The position of particle B with respect to A, I write it in this form: B divided by A is equal position of B minus position of A, because we would like to find it in respect to A. You remember I said if this is our origin, if this is the positive direction of the X, if it's like X is located there, I just simply said that that is the position of A. But even there, I said that we need to find it in respect, with respect to the origin. So the definition will be still correct. What is the position of the particle A in with respect to the origin? Based on this definition that I gave you, that is XA minus X0, not XO. We already know that this is the origin, so the value is 0. So whatever we define as a position of A with respect to the origin is perfectly fine. This is XA. Then we are able to find the relative position for two different particles, particle A and B, which is what I explained here. We can do exactly the same analysis for the velocity and the acceleration. Velocity of B with respect to A, acceleration of B with respect to A. They are exactly the same equation because we are just taking the derivative of each line. Let's see the example. So in this example, we assume that we have an elevator shaft, one single elevator shaft. There are two particles which are moving. So that's why I put two figures here. First of all, let's assume that this is the elevator cabin. It's moving upward with a constant speed, 2 meters per second, and at time equals 0, it's located 5 meters above the ground. In the same time, we have a ball located at 12 meters above the ground. We threw it upward with the initial velocity of 18 meters per second. You see these two particles, they are moving independently. So we are able to study the motion of ball and elevator independently. Let's start with the ball. When we throw the ball, the only acceleration will apply to the ball is the gravity. So that is the constant. Acceleration. We already learned if the acceleration is constant, that's a special case. So the velocity and displacement, we can just simply use those formulas. And then apply the numerical values because the initial velocity of ball is given, it's 18. And also this is the gravity acceleration, negative 9.8. So we are able to find the velocity of ball. We can do the same for the elevation of the ball or the position of the ball using that formula and then update the values. Initial position is 12 meter, velocity is given 18, acceleration is 9.8. Okay, that is the ball motion. Now we can talk about the motion of elevator. You might remember I said that the elevator is moving with a constant speed. You remember the special case when we have a constant speed. This is the way we are able to find the position is equal initial position plus vt. Initial position is given 5 meter, acceleration is given, sorry, there is no acceleration. Initial velocity is given 2 meters per second. So these two equations are the motion study for ball and elevator. Okay. Part A is asking us when and where these two particles will hit each other. We already know when these two particles, when they hit each other, there is an important information hidden there. They both have the same elevation in that point. So that's why we can simply put YE is equal to YB. We already found both those. We just put it as an equal value. And then this is the second, this is t power 2. We should find two values. The first value is a negative time, so it's not existing. The second value is 3.65. So if we put this time equal 3.6 in any of these equations, YE or YB, no matter because they are equal at that point, we should able to find the elevation. That's part A. Part B is asking about the relative velocity between these two particles when they hit each other. We already found the time, 3.6. What is the relative velocity in that point? It's very simple. We just simply find, let's say we would like to find the velocity of ball with respect to the elevator. That's simply VB minus VE. What is the VB? We can just use this formula. What is the VE? Is a constant value. It's perfect. Just update this time there. We should put time equal 3.6. Then we are able to find the relative velocity. It depends on the sign of this relative velocity. Please think about the relative velocity when they hit each other. Is it in a positive direction or in a negative direction? Think about this by your own. Of course, you can do it in your study group discussions as well. The last thing I wanted to share with you is the dependent motions. You remember in a previous example, two particles, they are moving independently, but there are some cases that we have dependent motion. For example, here, you see we have 4 pulleys, we have 3 masses, and then the goal is finding do the motion analysis of these particles. But the important thing that you need to know, at the end, they do not move independently. So particles A, B, C, they are in connection. And what is the connection? The connection is the rope. And we all know that the length of the rope is constant. Then we should find the relationship for the position of, relative relationship between position of A, B, and C. How? Let's start. I'm starting from, length of the rope. Can we say that length of the rope is equal starting from right hand side? That is this length. Let's say that this is almost equal to XA. And then it goes up. That is still XA. Okay, let's change the color. The rope comes down. What is this length here? We already know that this is my XP, so it's plus XP. It goes up. That's still XP. It comes down. That is XC. We can just simply combine those, so we can say that the length of the rope is 2XA plus 2XB plus XC. This is the relationship between position of A, B, and C, and you can see this is a dependent motion. We can just simply take a time derivative of that. The derivative of the constant is 0. dx over dt, this is the velocity, so that's why I'm able to write this equation. Also, the first derivative of the velocity, I should able to find the acceleration, and that will be the motion analysis of these dependent particles. Let's see the example. So in this example, we have 3 pulleys. We have color A, and also we know that we have this pulley here is connected to the color D. There are important informations are given. It's telling us that the color D is moving downward with a constant velocity. So the velocity of D is constant. What is the other information? It's telling us that at time equals 0, the color is located at point K, but then it will pass this 8" to reach out point L, and at that point, velocity of A will be 12" per second. So now we would like to determine the change in the elevation, the velocity, and acceleration of B. Look at this, all these inputs are on A and D, but what we would like to see is the output of particle B. But we already know that these are dependent motion, so as long as we find A and D, and as long as we find the relationship between A, D, and B, then that will be the answer for the motion analysis of particle B. Okay. But for now, let's start with the just individual study of color A. Color A is moving with it's telling that it moved with the constant acceleration. It's already given. Also, if you just read the text for the color A, it didn't talk about the time at all. So that's why you might remember this formula said relationship between velocity, acceleration, and displacement when the time is not involved, which is great. Let's put the values here. It already says when the color A reach out point L, the velocity is given. That is the velocity, which is 12. Also, we know the displacement of the particle A, it's 8" during that time. Okay, we can update this 8" here, and also the initial velocity is given. It's given in the text, that is 0. So everything is known except acceleration. Then we are able to find the acceleration of color A. Okay, that was the second equation in the special cases relationship when the acceleration is constant. V is equal, or initial V velocity plus AT. We already know the initial velocity of VA, it's 0. Acceleration, we found it, it's 9. So we can able to find the time, 1.3. This time here is the time it takes to color A comes from point K to L. Okay, that is color A. Let's continue with the pulley D. D is moving with the constant velocity. If this is the case, if this is the constant velocity, we already know the formula. X is equal x0 plus vt. We have no idea about the original position of this xt. We have no idea yet about the position of d, but the only thing that we know is the velocity of d, which is given, it's 3, so that's why we update it here. Okay, so just rewrite it in this way, we update it. And what is the value of t we would like to find? You remember in a previous slide, I said that color A is passing point K to L in 1.3 seconds. This is the time that we found. So we can simply update this time here. So we end up with this equation. And then since we have two unknowns, I'm just putting XD and the XD0 initial value in the left-hand side. Just keep it as this 4 equal 4 inch. The next step is planning to do the motion analysis of block B. But before that, we need to find the relationship between XA, XD, and XB. Do the same analysis. Find the length of the rope. Length of the rope, that is part XA plus. It comes down here. This length here is equal XD. It goes up. Look at this rope. That is XD again. And then it comes down. This length here, that is my XB. So at the end, that will be my L rope. This is XA plus 2XD plus XB. And since this is a constant number, we can say that just simply the original position of XA, XD, and XB, when we just write it based on the length of the rope, that's exactly, it should be equal to the position of XA, D, and B at any time, because all in all, that will be the constant length of the rope. So that's why I'm able to write it in this form. So this is the initial value. This is the current values for the positions. They are equal because they are lengths of the rope. What I can do, I can just simply rewrite that equation. For example, put XA and XA0 together, XD and XD0 together, and the same for the XB. Okay, so XA minus XA0, we found it. This is 8. We didn't even found it, it's given. The color A traveled 8 inch. XD minus XD0, we found it in a previous slide. You remember we said that we have two unknown, but the ultimate displacement is 4 inch. Plus some value that we have no idea about it. Displacement of particle B. When we solve it, we are able to find the displacement of particle B, which is negative 16 inch. So it seems that the particle B is coming down, equal to 16 inch. Then it's asking us what is the velocity of block B. We just simply take the derivative of the first line. Right hand side will be 0. So it's a time derivative. So it's this one. VA at this point, it was given, it's 12 meters per second. It was in the text. VD, we found it in the previous slide. It's 3. And then VB is unknown, so we are able to find VB as well. Okay, so that's all I wanted to share with you. So in the next lecture, still I will continue this chapter, kinematics of particles. So I think you are able to start to work on the homework problems as well. And as I said, when you want to deal with the homework problems, all the time think about we have only few formula, definition of velocity and acceleration, and also a couple of special cases where the velocity is constant or where the acceleration is constant. Everything started from that point. Whatever is the problem, we should able to find it using only those few information. Okay, thank you and see you in the next lecture.